Okay, so moving on now to Chapter 2. We're going to start actually in Section 2.3. We're going to see some ideas in 2.3, get some geometric intuition for those ideas in RN. And then we're going to define a more abstract context, and having described that more abstract context, we're going to revisit these ideas in the more abstract context. But I think it's good to start with some geometric intuition first. So we're going to start off with this thing called span, the span of a collection of vectors. Definition is very straightforward. It's just a collection of all linear combinations of those vectors. All the linear combinations, every possible linear combination. So let's start with a simple example. Consider the span of a single vector. Single vector there. Well, what are all the linear combinations that you could get out of this one single vector? Well, there's nothing to add. All we can do is scalar multiply, and all scalar multiples of a single vector, we're going to give you a line. Okay, now this is with the understanding that this single vector is non-zero. Of course, if the vector is the zero vector, then all the multiples of that zero vector are still the zero vector, so in that case you don't get a line. So only for a non-zero vector. Okay. So what about a pair of vectors? And let's consider the case where these are non-zero vectors, and let's further consider that they're not parallel. So given a pair of vectors, the span, collection of all linear combinations of those vectors, well, if you think through all the different cases, well, we're going to have all multiples of that v vector, but we can also add to all of these multiples of v, we can add any multiple of w. Any multiple of w at all can be added to those all possible multiples of v, and so altogether you're going to get, one would think, the geometric intuition anyway, you'll get an entire plane. We call this the plane that is spanned by those two vectors. Okay, now importantly, we were considering that these vectors are not zero and not parallel. Now let's think about why is it important that they were not parallel. Well, if you come down here and consider the case where they are parallel, we have a vector v and a vector w. Collection of all scalar multiples of v is that, but when you start adding multiples of w to that, well, you're still on the same line because you're adding vectors that are parallel to these existing vectors. So in that case, you don't get a plane. So if they are parallel, you just get a line. You can consider likewise what would happen if one of these vectors was a zero vector. Okay. All right. Now that's just geometric intuition, and let's think about from a more algebraic and precise point of view. Let's consider this pair of vectors here. Note that these are non-zero. Note that they are parallel. So this is a pair of non-zero, non-parallel vectors in R2, and one would think then that they span a plane in R2. In other words, that they span all of R2. That's the geometric sense. In other words, you have this picture in your mind, and 1, negative 1 is like that, and 2, 3 is like that, and all multiples, and gosh, it really does feel like it should give you all of R2. Okay. How do we prove that algebraically? Well, I need to show that every vector in R2 is in fact some linear combination of those two vectors. Right? That's exactly what it would mean for this span to be all of R2. Every vector could be written as a linear combination. Well, let's say it like this. Every vector is in this collection of all linear combinations of those given vectors. Okay, so this statement we've now rewritten as a vector equation. Now, let's look at this vector equation and realize that we can look at it one component at a time. Let's think about the first component. The first component of this vector equation is that equation. And likewise, the second component of that equation is that equation. So if this vector equation is going to be true, another way to say that is that both of the coordinate equations individually have to be true. Said differently, this system of equations has to be true. Or, said even differently, this matrix equation has to be true. So interestingly, this statement about span, the collection of all linear combinations, we were conceiving geometrically, like this. We've shown now that it can be reduced to a matrix equation that we need to understand. Specifically, I need to know for every vector B, I need to know that this equation can be solved for this vector C. Right? So, said differently, I need to show that this matrix has the existence property. So again, another flashback back to chapter 1. Okay, so does this matrix have the existence property? Well, you can row reduce it and check to see that there is, hopefully, fingers crossed, in fact, a pivot in every row. And that will confirm that this matrix has, as needed, the existence property. Now, much more clever than that is to observe that this matrix is non-singular by observing that the determinant's non-zero. And that's a real nice application of our facts about determinants, and equivalent facts about non-singular matrices. So the determinant in this case is 5. And 5 is not 0. Therefore, it's non-singular. Therefore, this matrix has the existence property, and therefore, we have a solution. Okay. All right. A little bit of lingo, and I've been catching myself using this lingo as we've been discussing this topic, and that is, even though span was defined as a noun, we can say that a collection of vectors spans. That's now being used as a verb. Spans a set. If every vector in that set is in the span. Just a little bit of lingo.